Now?
Yes.
Yes?
Oh, perfect.
So you see the screen and me. What
Yes.
else do you want?
Perfect.
Okay, then time to start.
So I will also start the recording then, and we're very happy to have you. So
Recording in progress.
welcome and please go ahead with the lecture.
I can start? Okay, welcome. I will tell you this morning about water smart hydrogen and what it means. Here it says a sustainable way of producing hydrogen, and it's part of the Electrode water smart hydrogen, and I started with that a bit more than 3 years ago. And I'm going to introduce you in the topic what actually this means. Now I try to wait a moment.
Touching the screen, maybe?
I try to advance now the presentation, but that's something that was working before.
You touch?
Right this moment you see the first slide, you can
And
continue.
with the mouse? And the other?
There's one little issue that the screen doesn't continue, and that was working before.
If you press the left in the mouse,
Yes. We fixed this with the left mouse click. Now, I will first start with state-of-the-art electrolyzers, and perhaps you can close the door.
Yes,
Okay,
sure.
thank you. Now, the point is that with all state-of-the-art electrolyzers, and I will show you just in a second, it all need pure water to make hydrogen gas. And that is really one of the issues. When you want to do this on a very large scale, you need very large amounts of pure water. And here are the four examples of the state-of-the-art electrolyzers. Some are in development, some are really used in practice. There are four types. It's on the left top, we see the alkaline electrolyzer that uses a high pH electrolyte, actually an alkaline solution of, in practice, 300 grams of potassium hydroxide per liter, so very strong alkaline. And you see here the anode and the cathode reaction. So on the anode you make oxygen, and the cathode you make hydrogen gas. And we will use later on this picture, because I will come back on this. And this technology is there for about 100 years. A very modern technology is on the right top side, where you see the proton exchange membrane electrolyzer. That's the text here behind the green. And there you have a proton exchange membrane. That's actually what's called the letters PEM, proton exchange membrane, where you have the oxidation of water to oxygen and protons. The protons go through the membrane and are being reduced at the cathode to hydrogen gas. Similar than the proton exchange membrane electrolysis is the anion exchange membrane electrolysis, where there is no actually electrolyte solution with potassium hydroxide, but we use here pure water. And this is still under development, where you have here oxygen evolution at your anode and hydrogen evolution at your cathode. And a complete different type of electrolysis cell is a solid oxide electrolysis cell, where you see that you have the oxygen 2- anion that goes through a solid electrolyte at high temperature, is making again oxygen at the anode and making hydrogen here at the cathode. And in this case, you do not make hydroxide ions, but O2- anions that go through the solid electrolyte. So this is a complete different way of making the electrolysis cell. So both on top are now what is more or less common in practice. one uses non-noble metals, the right one uses noble metals, the PEM electrolyzer. That makes this electrolyzer also the most expensive one. Here you see an example on what scale they make actually these electrolyzers. This is the proton exchange membrane electrolyzer, and it's 6 megawatt. Actually made here of 6 modules, because you can see them here standing. And then, yeah, you see them, there's relatively small footprint, and that's because the current density for these type of electrolyzers is huge. Can be 10,000 or more amps per square meter. So you need only a very small footprint to realize. So that is the advantage of the proton exchange membrane electrolyzer. Also that you make a very pure hydrogen gas. Another example is the alkaline electrolyzer. This is a 10 megawatt example. And you see this is a huge installation. At the moment the largest stacks are 20 megawatt. They are being installed in Rotterdam in a building of from Shell, because there they want to install 200 megawatt installation, and that are 10 units of 20 megawatt. Now this is a 10 megawatt installation, and you see there is much more than only the stack that you can see there, because there's a lot of instruments around. And this uses the alkaline technology. And you see, bottom line, pure water is needed here. Now, this is for the north of the Netherlands, and there's a lot of discussion there. The ambition is to have 10 gigawatt hydrogen production, so based on energy made by windmills, so they need a windmill park there. And they want to produce their hydrogen, and the hydrogen is being transported by a huge transport line through the Netherlands and to the place where it's needed. And that will first go to industry. So that's the planning there for the north of the Netherlands. There is some discussion now about whether or not they're going to put there the windmills because of the landscape. It's like in Friesland, but also in Groningen. They do not like to see windmills in the landscape, but you have to put them somewhere. But this is the ambition they have there. And you see, Shell is also involved there, and GasUnie. Now it comes to a more discussion about what you need to make an electrolysis cell. Now, the PEM electrolyzer, as explained, is actually the Rolls-Royce under the electrolyzers. It has a small footprint. It uses very high current density, 10,000 to 40,000 amps per square meter. And that's because there are really good catalysts inside. And these catalysts actually are based on iridium and platinum. And now it comes. Do we have enough iridium and platinum on this planet? The answer is actually no. Because we call them critical raw materials. They are part of the platinum group metals. And you see, actually, for platinum, there are only very few producers. South Africa is with 70%, then comes Russia, and a bit of Zimbabwe. And then a little bit is left. So we have only very few countries who produce platinum. The same actually applies for iridium. And why iridium and platinum are connected here in dark blue? Because iridium is a side catch of platinum. So there is a little amount of iridium. But iridium is needed not only to make the catalyst for the proton exchange membrane electrolyzer, but also for other technology. So there is a large demand for iridium, and it's a very small supply. That makes it critical. And also critical to roll out the technology of the proton exchange membrane electrolysis worldwide. And there's another issue, that for the PEM electrolysis cell, you need very pure water. And I will discuss this first. Now, the PEM electrolysis. You have to focus a bit more on this. In order to be able to roll out this technology, you would say lower than the loading, and that's the amount of catalyst in milligram per square centimeter, for instance, that is needed for the anode and the cathode, so lower the loading, and then you can have less critical demand on this platinum and iridium. So what shows the table is nowadays the current density is 2 amps per square centimeter, 20,000 amps per square meter, and you want to go there to 50,000 amps per square meter. That's really high current density. And they want to enlarge the single cell area, 1,200 to 5,000 square centimeter. But now comes the critical things. The iridium loading, and you can express it in milligrams per square centimeter or in grams per kilowatt. And you see what they want to do. When we look at milligram per square centimeter, they want to go from 5 to 0.2. So that's 25 times less. And also for platinum, they want to lower it a factor 5, as you see here in kilowatt, but here you see also really strong lowering of the platinum loading in milligrams per square centimeter. So also very strong lowering. The question is, what happens when you do this? First of all, the catalytic activity will more or less remain the same, but the lifetime, so the number of hours you can use this proton exchange membrane electrolysis cell will be much less. So of course, for economic reasons, you can say we lower the loading strongly, but the lifetime will be much less. Because otherwise, like for instance dimension stable anodes, you would put a much lower loading. And of course it's possible, but you have immediately a lower lifetime. So this demand is so strong that in my view, you can lower the loading, but your lifetime is cut. And that is a problem. So you have to fix then the lifetime. Here you see again the iridium and platinum loading on the proton exchange membrane electrolyzers. Now the loading can also be expressed in grams per kilowatt. That you put the power you put on the electrolysis cell, and you see here at the moment the total loading is almost 2 grams of platinum and iridium together per kilowatt. And the demand of the European Union is to lower this loading to this value and keep the same catalytic activity. And I would say yes, that's possible, but not in lifetime. So these two things are conflicting. Now, there is, I must say, there was a European call for new projects, but yeah, the project we formulated, and I will come back on that later, by itself, they found that okay, but the problem is there are so many applicants for one project that we did not make it. However, I want still to put their demands. And that were the demands for direct seawater electrolysis. So not for the PEM electrolysis, but the direct seawater electrolysis. Means you do not make pure water in advance. You use seawater as it is. So you can do this at sea. There they have other demands as for the PEM electrolysis and alkaline electrolysis. And the demands are here. At the cell voltage of 2 volt, they want a specific energy of 53.2 kilowatt hour per kilogram of hydrogen. And the only thing you need to do then is to make a graph of this kilowatt hour per kilo hydrogen, so actually the specific energy versus the cell voltage. And you see that that demand, when you look then at 2 volt, there's actually this point here. This is the 53 kilowatt hour per kilo. So actually, I translated this specific energy demand towards the cell voltage, because they did not say the cell voltage. And of course, you have to calculate what the cell voltage is, because you need this cell voltage to see when you make an electrolysis cell how close you are. And another thing that was connected to it is the current density. So they require actually more or less a current density about 5,000 amps per square meter. And then together with this cell voltage, you get this specific energy. The cell voltage is important here. And of course, below the 1.23 volt, you do not make any hydrogen gas at all. So you see you have a little bit less than 0.8 volt to realize this, this demand for hydrogen. And I used to calculate this an internal resistance of the electrolyzer of the single cell of 0.1 ohm square centimeter, because you need to know, of course, what the ohm loss is inside. Now, when we want a future on hydrogen, not from methane, but from electricity, because when you use methane to make hydrogen gas, that's done at the moment. 95% of all the hydrogen used in the world comes from methane. But when you do that, you get also CO2, carbon dioxide. And that's of course no solution, unless you do something with the carbon dioxide. But when you use electricity, you need to know how much pure water you need when you do not use seawater. So I calculated here how much pure water you need for a 10 gigawatt electrolysis, like was shown before for the north of the Netherlands in the Eemshaven in Groningen. So the power is 10 gigawatt. The cell voltage, as discussed, is 2 volt. Now I calculate how much pure water is needed per day when you apply a power of 10 gigawatt. So the pure water you need per day is 40,000 cubic meters per day. Now we have a pure water factory in the Netherlands, in Emmen, and they produce pure water. They produce at the moment maximum 10,000 cubic meter pure water per day. So actually you would need then 4 pure water factories in Groningen. Although there is not enough water available, you would need an equivalent of pure water, 4 pure water factories. So when you look at this, how much you need, and that's only for 10 gigawatt. I mean, we would need in the Netherlands at least 100 to 300 gigawatt. We would need much more power. Then I can say the conclusion is we have to prevent drinking water stress by using seawater. When we would use our drinking water on a huge scale to make green hydrogen, as we call it, we have the green hydrogen, but we have another problem, namely scarcity of drinking water. So actually, we do not want to solve one problem and create another problem. That is here the conclusion. So we have to do something about the water. And we have to realize when you want to make hydrogen, you need water. And that is not the water we use for our drinking, as drinking water. So we need to find a solution for that. So, at the larger scale, and I mean the larger scale means more than 100 gigawatt, the use of pure water will lead to a drinking water stress. And do we want that? No. So, the electrolysis on that scale should not interfere with our water supply. Now, the solution is, at sea, we have a lot of water, but we also know there is a lot of salt in the water. So we can't use directly this seawater. And now it comes, actually we do not want additional desalination at sea to make pure water. And there is a simple reason. There's a lot of debate going on at the moment. Why would you ever use seawater, direct seawater electrolysis, when you can first desalinate seawater? And at land, of course, you can do it. There are countries like Spain, countries in the east, where they use seawater for drinking water. But all these installations are at shore, at the land. And there is a lot of people around to keep it working. So the question is, the people who say 1% of the total energy needed to make hydrogen is for making pure water from seawater, they are right. But they are not right in the fact that you can do that in remote conditions where nobody is around. So the question is, can you do stand alone with nobody around, make pure water from seawater? And the answer is no. So there is another reason that we want to look at direct seawater electrolysis. Can we make use of seawater without desalinating seawater first? And can we do that with, actually in remote conditions, stand alone, with no people around? That is the question. So it has nothing to do with this 1% of energy, nothing. And that's the strong debate in the literature and in politics at the moment. Why would you ever do direct seawater electrolysis? Because you can't do standalone desalination remotely without any people involved. That is at the moment the answer. So we have to look. So, how to make an hydrogen without pure water? Is there an alternative? Now, worldwide, more than 97% of all the water is seawater. You can't put it in an electrolysis cell we have at the moment. So, the question is, can we use seawater directly or in whatever mode? Because that is the question. So, the question is direct seawater electrolysis possible? And this is the abbreviation normally used. DSWE. That is the abbreviation in literature. That is the question. So that is what I started with 3 years ago, this question. Now, I had to put some demands there. When you would have a swimming pool at home, for instance, you really need now and then to purify your water. And that means you need to make actually chlorine in your swimming pool. Add chlorine or to make it in situ. Now, that starts already with the first issue. When you have two electrodes and when you put them in seawater, then you see that you make chlorine at the anode. When you have at least an electrode that does not dissolve itself, you have chlorine at the anode. And at a huge scale, this is really something you do not want. Another thing is, when you take seawater, you go to the sea, you put two electrodes in, you have a battery with you, you see another phenomenon. At the cathode, at the negative pole, you see scaling, calcium carbonate, magnesium carbonate. And then the party is over very soon, because the whole electrode will scale and your current will go down. So that's the second point, we do not want scaling. Another thing is, of course, the biofouling. The sea is alive, so you have to be able to do something with the biofouling. After some time, your electrodes will be fouled with a biofilm layer. Then something that's very critical in my view, the crossover of hydrogen at zero current. All current technologies exist because you need to keep a load on the system. What I mean is, when you start this electrolysis cell, the proton exchange membrane and the alkaline electrolysis cell, there's something funny that happens because you can't turn down the current. When you go down, completely turn down the current, hydrogen will go from one side, the cathode side, to the anode side, and you get an explosive mixture. In other words, your whole electrolysis system becomes a bomb. It can explode any moment. And that is very critical. So although they did not solve this issue, these systems are on the market. So that is a very critical point. Whenever you start from scratch again and you make a new system, this is on the demand list. You must be able at any moment to turn off the current, because a windmill is not always turning. And that is a very critical point. Now, what they said is platinum group metals, that is a group of 6 metals, platinum, iridium, ruthenium, palladium, osmium, rhodium. These 6 metals are rare. Not only rare, also very expensive. And actually, you would like to avoid them, because that makes the electrolyzer very expensive. Now, another thing is anti-scalants. The people who desalinate seawater first, pure water, use anti-scalants. And these anti-scalants, they land in the sea. At the end, they come into the sea. That's really something you do not want. Of course, that is kept a bit secret, but they use anti-scalants. Because otherwise you add scaling. We do not want anti-scalants. When you do not use platinum group metals as an anode, as a positive pole, you get corrosion. And of course, you do not want corrosion. I'm not going to explain the mechanism of corrosion here, but you need to know the mechanism of corrosion to keep your electrode in one piece and not dissolving. So this is actually, in short, and there are 7 points, your wish list. Actually things you really do not want to happen. Now, so what needs to be done? You have a short list, like a shopping list. So first of all, as explained, desalination does not go without people. So the first point is, can we make use of no desalination? So not making ultra pure water first. That's the first line. And of course, we do not want chlorine evolution at the anode. Otherwise, the whole North Sea will be a chloride factory. And we do not want that because chlorine is very poisonous gas. Of course, no scaling at the cathode. So no calcium carbonate or magnesium carbonate formation at the cathode. No biofouling of the system. That's another point. And no crossover of hydrogen at zero current. That was not solved, we have to say that again, in the nowadays technology. When you buy an electrolyzer, and a lot of electrolyzers are made in Europe, but also a lot nowadays in China, this technology that's now being made, I still cross over hydrogen towards the anode where the oxygen is. And hydrogen and oxygen together, you can try it out, but do it on a small scale because you get an explosion. And on a large scale, it's really strong. We do not want to use the platinum group metals, these very select 6 metals. Of course, no anti-scaling, so there's enough poisoning already of the sea. And of course, the anode should not corrode. So we have to take measures inside to prevent corrosion. Now, the demand for the direct seawater electrolysis. Now, normally at the anode, platinum and iridium are used. These are the 2 platinum group metals. So we do not want to use these metals. And actually, the scaling issue is often solved by adding from the outside acid. So we want no external acid being used. So you can't go there in the middle of the sea with acid to try to solve the scaling. So whenever acid comes into play, no external acid. So you're not bringing the acid towards the electrolysis cell. And also no use of anti-scalants. I mean, forbidden. Like they did, for instance, in Israel, they did their seawater electrolysis. However, they first took magnesium and calcium out. That's a big effort. You say, I don't want scaling, I don't have scaling, but they take first magnesium and calcium out. Another thing is then you don't have scaling, but you can still have, of course, chlorine evolution and corrosion. But yeah, I think it's not the way to go, take magnesium and calcium out. It's really a huge undertaking because there's a lot of magnesium and calcium in the seawater. Now, we need to get pure water out of seawater, but not by desalination. So it means we need to find another trick. That is then on our to-do list. We need to find another trick. And that is below. So what we are going to do is extract water from seawater. And that I have to explain. Desalination means you take the salt out of seawater. And what you get is very strong salt solution, we call that brine. And that in huge amounts, when you put it back in the sea, and everything where you put it back dies, because there's so much salt in the water. Wouldn't it be more clever to take a little bit of water out of seawater, make the seawater a little bit more salty, so everything what's around stays alive there in the Dead Sea, except a lot of salt. So I want to take a little bit of water from seawater and then make the seawater a little bit more salty. Then all the life in the sea remains there instead of making a sea with no life anymore. Now, rules to extract pure water from seawater. Are there a possibility? Yes. A possibility that's done there for many years, we call that membrane distillation. And you need some kind of heat source. That can be the electrolysis cell itself, that is done at Wageningen University. Actually, they take their PEM electrolysis cell Well, the PEM electrolysis cell, as explained, is not the way to go because we don't have enough platinum and iridium. Anyhow, they took the PEM electrolysis cell, the heat generated inside is used for membrane distillation. That was invented many years ago at the Dutch Institute of Applied Research, TNO, and they call it their MEM still, but membrane distillation is also a modern variant for the electrolysis. I'm not using that route. Of course, what I explained, electrodialysis, the conventional route, plus a step to make pure water like reverse osmosis, and also use antiscalants. I'm not going in this route because it's not maintenance free. It is, German will say, wartungsfrei. It's not. You need people around. And you can't send people to thousands of locations at the sea. So I'm not taking this route. Then comes route number 3. I have to attract pure water from seawater. And that can be with a phenomenon called osmosis. So what we are going to use is, we can use ion exchange membranes and a higher ion strength. So we need a salt solution, an electrolyte, with more salt in it than in seawater itself. And we can also use a water depleting mechanism. I will come back to this. Now, so we use the rules 3A and 3B to extract pure water from seawater. And we can do this with ion exchange membranes plus a higher ion strength. And we can do this with a water depleting mechanism. Later on, I will more clarify this. First, the way we want to do it. When you go back to the proton exchange membrane electrolysis cell, that is the one that uses pure water inside. So there is no potassium hydroxide inside. However, pure water has a higher vapor pressure than seawater. Simple, because there's no salting. So pure water will never attract water from seawater. That's impossible, because it has a higher vapor pressure and seawater a lower vapor pressure. And then they're exactly the same, but that was in the bottom left, the anion exchange membrane electrolysis that also uses pure water, but then an anion exchange membrane, also there, the pure water will never attract seawater. And then the other way, that was on the bottom right, the solid state electrolysis at high temperature. The temperature is far too high there to use seawater. So what we see from the 4 forms we had in the beginning, one is left. So the question is, which current electrolysis system obeys the rule? No, only the alkaline electrolysis system. So the alkaline electrolysis system is the one we will continue with. And the question comes, how to combine the alkaline electrolysis system or a kind of variant from this and seawater. Now, first of all, alkaline electrolysis systems use no noble metals. So the platinum group metals can stay where they are, we don't need them. That is a good thing. And also, alkaline solution prevent chlorine formation. Another important point, in an alkaline solution, you do not make chlorine. And that's because of the difference in oxidation potential of OH- and chloride. So the question comes, how to supply the alkaline electrolysis cell with pure water? And how to combine it with seawater? So that is actually the question. Here is the alkaline electrolysis cell. And the question is how to modify this to seawater electrolysis. First, I made my drawing myself. So on the left, you have the anode. You oxidize the hydroxide ions towards oxygen and water. Then you have a membrane in the middle, we call it M, and the membrane passes the hydroxyl ions towards anode. Anions always go to the anode, and cations go to the cathode. That is a simple rule to remember when you don't know anymore where the ions go. And at the cathode, water is being reduced to hydrogen and hydroxyl ions, and then I put the half reactions there for the anode, so the oxidation of hydroxyl ions, and at the cathode, the reduction of water, and the net reaction is very simple. 2 water give 2 hydrogen and 1 oxygen. Now the question is how to modify this, because we know we need to add pure water to this, and we know we have very salty water in a bucket in front of us. That's the seawater. How to do that? That's the question. We have a link that is missing. And one of the possibilities, because when I started to do this 3 years ago, I thought it's quite impossible, this question, but after more than 3 years, I realized there are a lot of routes towards the answer, a lot of routes. One possibility I'm going to explain, and that starts simple. We have here what we call a bipolar membrane, BPM. That's actually a membrane made of 2 layers, an anion exchange layer and a cation exchange layer, given as A and C. And that membrane has a very specific property. It splits water in OH minus, the hydroxyl ion, and a proton. Actually, the normal water equilibrium, everybody learns at the secondary school. Water splits in H plus and OH minus. And that are in equal concentrations, and normally pH is 7 of our drinking water, because it's not acidic or alkaline. So bipolar membrane splits it in these 2 ions. So it's a water splitting membrane. And then all of a sudden, from a simple graph to this. And I need to show this, because this was my first master student, Alice Donker, and we made this setup. And in the beginning, we were very happy with it. Now, what do we recognize? First, we look in the middle. We see an anode and we see on the left, and we see a cathode on the right. And actually, what we did is we are making a new heart into the alkaline electrolysis cell. And this heart becomes a bit more complicated as it is here. What we did is we made now 2 of these water splitting membranes here. You see 2 water splitting membranes, the left and the right. And on the left you see the water splitting membranes make hydroxyl ions, and these hydroxyl ions are being oxidized to oxygen. And on the right we see that protons are made, and here we see that water is being reduced to hydrogen and hydroxyl ions. And actually the reason to make it in this way is that we put seawater in the middle of these 2 bipolar membranes. So we do not put here seawater in contact with the anode or the cathode. There's a possibility to use it as well, but we do not do it here. So there's no direct contact of the seawater with the electrode, but it's in the middle. And it goes in between the 2 bipolar membranes. Now, when we look carefully, something is happening. In the middle, where the seawater passes, we see on one side protons are being made, so that means that the surface of this membrane becomes low pH or acidic, and when the low pH is, you have no scaling. But on the right side, you see OH minus, so hydroxyl ions are coming out of the anion exchange layer of the right BPM2, so the right side bipolar membrane, and there you get a high pH surface. Now, we run this setup for 10 days at 1000 amps per square meter, continuous, day and night. And then something happened. In this layer between the 2 membranes, we saw a kind of soft deposit. Call it a kind of toothpaste. So it was a soft deposit. And the soft deposit was slowly growing from the right side here of this bipolar membrane, because it's a high pH, and it was actually filling the complete compartment between the 2 bipolar membranes. And that needed a solution. But that we realized at the end of her thesis that something was missing. And then it becomes a bit more complicated. First, what we noticed. The question is, electrolysis of seawater, which we call it the double bipolar membrane technology, does it work? We can say it worked 10 days, 1,000 amps per square meter, 24, so 240 hours. That works, so it's not a short-term experiment, 10 days. We also see that the alkalinity at the anion exchange membrane side of the bipolar membrane, that was on the right side, results in a high surface pH. Now, seawater, we all know from the shells in the sea, contains bicarbonate, later forms that calcium carbonate, so bicarbonate reacts with hydroxide, makes carbonate. Now there is enough calcium in seawater, so you make calcium carbonate. And it was a soft kind of deposit. And it also, of course, contains a lot of magnesium, so you get also magnesium carbonate. So the challenge is, and defined here, solve this scaling using no external chemicals. And is there a solution? Yes, I say solution, I don't say yet how. The scaling was solved using in-situ acid cleaning. You will make something in situ because we decided not to buy acid. And the result was that we found actually 2 patterns at the end with the solution. Now I'm going to click, because it comes another, there comes here another setup. Drawn schematically, we see on the left side the anode, on the right side the cathode, and we see back again the 2 bipolar membranes. So I put here the water splitting on the left and the water splitting on the right. So we recognize this part, we recognize this part, and we see there are 2 bipolar membranes. We see there is a membrane in between. So the heart inside the alkaline electrolysis cell gets now 2 chambers. So there are 2 chambers. And the chamber has a very special membrane M in the middle. Because, as I explained, when you make protons here on the left side in the left chamber, here in the middle, you will not get scaling. However, these protons are needed. And what I need is I don't pump away. So there's something happening. Here I make hydroxide ions, and yeah, seawater comes in from the bottom, goes to the top on both compartments in the middle. So actually, this high pH you get from hydroxide ions, these hydroxide ions must be pumped away. Then I got a lot of questions when I showed this scheme, because you would say, from a simple reasoning, you make the same amount of hydroxide ions and protons, and then you keep neutral pH, you will never have scaling. In opposite way you find in practice, you get scaling on this side. So the question is, how can I contain, and that's actually the word, how can I keep the protons in the left compartment and use it to solve, to dissolve here the scaling on the right side? And that's the question. Now, this membrane is an anion exchange membrane with a special property, namely that protons cannot pass towards the cathode, that's on the right. So it contains the acid. And now comes the trick. So it has 2 tricks inside. First, we have the 2 chambers, then I take a membrane that keeps the proton inside. It's actually an anion exchange membrane. And another thing is that this volume here is kept there. That means I keep pumping on the right side, but now and then I stop pumping on the left side. And that I make in situ acid, and that acid is pumped towards this compartment to make temporary low pH and solve the scaling. And I'm going to, yes. So we try this out at 1500 amps per square meter for 4 hours. And we see this is the cell voltage, and we have 3 membranes, bipolar twice and a special membrane. Of course we have the anode and cathode. And we arrive at a bit more than 5 volt. And actually we don't have seawater at any electrodes, we do not allow that. We have them in between membranes, And the big question is, why do we get here a stable voltage? And that's because of the following. I'm almost at the end now. This. You do have to do some calculation, because you can calculate nicely in Excel, for instance, how much acid you make, how long you have to wait, what's the volume of your compartment to make a pH that is lower than 3. I found in a master thesis from the US a very nice report that when you want to dissolve calcium carbonate in situ, your pH has to be less than 3. Of course, you need to calculate then how much time it takes at this current density. And that was for a larger stack. This was a stack where it was 60 amps, so 60 ampere was running the stack at this current density. And the question is, can I go lower than pH 3? Now, this is the pH of the liquid coming out of the right chamber inside. So that was the bipolar membrane on the right, that chamber next to it. This was the water coming out. And you see, the pH goes almost as low as 1 here. And that means we can completely dissolve the scaling by the acid actually made in situ. And when we mix then the streams coming out of both chambers, we have neutral pH, of course, again. So with this, I call it a pH swing. We can solve in situ the scaling. Now, the conclusions, I'm almost through it. Seawater can be used as pure water without desalination, because I did not desalinate. What I do is I extract some water from seawater and we make the salinity a little bit higher. When you know the Waddenzee here has a salinity that changes between 20 and 30 grams per liter. So you see nature can really live with a bit change in salinity. Now, the work done and shown here was patented in 2 Dutch patents, and they are shown here. So that has to do with the 2 bipolar membranes with a membrane in between, so 2 chambers actually, a new heart, I would say, in the electrolysis cell, alkaline, and the in situ acid cleaning was also put in there. So the scaling issues have been solved in situ. Pure water was extracted from seawater, so I make the seawater a bit more salty, but I don't make brine, and brine means you get something like 100 or 200 grams per liter of salt in the seawater, and that means no life anymore. I use no platinum group metals because it's an alkaline electrolysis cell. In an alkaline electrolysis cell, you typically use nickel and iron, and these are not rare. And another thing, and that is very important, I can switch off the current at any moment, because from the anode to the anode, from the anode to the cathode, there are 2 compartments in between with seawater. You don't have crossover of hydrogen. So this cell can be switched off any moment. And actually it's a revival here of alkaline electrolysis because, yeah, it has been changed into a triple membrane technology. Of course you have all kinds of variants on this work, but in this case we have 3 membranes installed. And of course, to further lower the cell voltage, it's the field of electrocatalysis. And electrocatalysis means you put a catalyst that makes it easier to make hydrogen and oxygen, a gas. So with the electrocatalyst, you make the cell voltage lower. With the example shown, actually, we solved all the issues we had at the start. So we have no chlorine formation, no scaling, no platinum group metals, and we don't make brine. And we use seawater as it is. Now, when you would have any questions, this is my email address, michel.saakes@wetsus.nl, and this is my phone number here below, so you can always contact me when you would have any questions, because yeah, there are not only this route, there are many routes now available after 3 years for using seawater for making green hydrogen, and it means not making use of drinking water and not making use of the platinum group metals. because we can avoid them when we have a good design, as you show, of the cell. So whenever you would have questions, contact me, and I thank you very much for your attention. And made it in an hour. Any questions online?
Thanks, Michel.
Yeah.
Can you hear me?
Yes, I can hear you loudly.
Okay. It was quite interesting again. So I've learned some more new things that I didn't know before with what you're doing.
Yeah.
So my question, let me see. My question is about the issue of, because I see there are some people here also online from, I see Mr. Dekule, he's actually from Nigeria. So with this, what you're doing, this technology, is it something, looking at the African context, for instance, where everybody's thinking about using, talking about desalination and desalination and desalination.
Yeah.
What prospects does this have, this direct seawater electrolysis have beyond Europe?
Now, the point is, when you do not have access to drinking water or pure water for your electrolysis system, the reason why we do this is we want really to show that when you have only seawater that's available at the coast, you can still make hydrogen, and with hydrogen you can make all kinds of other products, when you would have only electricity. Electricity to run the system and seawater as a water source. That's actually the reason why we do this. And I've shown here one example, but in the meantime we have learned a lot about other possibility as well. So you can make a system like this, you can a bit more hybrid systems, there are all kinds of different possibilities. And what was rare in the start, because direct seawater electrolysis systems have been proposed at a lot of places in the world, but what we see all the time is that these systems proposed actually have issues. I mean, there are issues that show that they cannot function. And we want to show that with some modification of existing technology, you can make use of seawater. So it's very important. You can also make use of a bit salty water. Suppose you use water with 5 or 10 grams per liter of salt inside. You can also use this water. So there are different ways you can use seawater to make hydrogen gas. And with hydrogen gas, you can heat your house, you can cook on, you can put it in your car, you can also change it to methanol or formic acid. There are a lot of possibilities. But most important, when you do not have access to surface water or water with a very low salt content, you can just use seawater. That's actually the reason why we do this. And you do not need to desalinate. That is also an important point.
Yeah.
So it's just to make use of what nature has, and most of the water is salty water, as I show you. More than 97% of the water we face it in this world is salt water. And what would be nicer than use salt water as it is, without the need to desalinate? Because technically, of course, you can desalinate, but when you can skip this whole desalination technology and still use salt water, it makes the system more simple. The less steps you need to make what you want, the better it is. That's actually also what I want to say. Yeah.
Thanks very much, very clear.
Yeah. Are there more questions from online?
I have a question. Thank
Yeah.
you very much, Michel.
Yeah,
Very
please.
interesting talk.
Yeah.
At the end, everything came together. So I switched the light in my brain. It's like this.
Yeah.
I was very intrigued by the pH graph and the time scale at which you change the pH. Is that something you are looking into what is the optimal time to run the system in one pH and the other?
Now I will say that the scaling that happens inside the right chamber of the new heart inside the alkaline electrolysis cell, that scaling takes days before the compartment is filled. So what you have to do is, I decided to clean this compartment as often as possible. And when the compartment gets thinner and you have that membrane M in between, that is actually a proton blocking anion exchange membrane with low thickness, then you can calculate what your pH will become when, for instance, you decide for, say, half a minute to save all the acid in the left chamber of that middle compartment. And when you pump that then to the right chamber, well, you keep on pumping the seawater to the right chamber, you actually can measure the outgoing pH of the right chamber there. And then you see that pH, so I calculated at home, how much time do I need to really go below pH 3? And then I decided, well, perhaps I can go even below pH 2 and really clear all the scaling there. But you do not only do the scaling, it's a twofold action. You also disable any biofilm to grow, because biology needs some kind of stable conditions. When you switch all the time from a neutral pH, from high pH to neutral pH to low pH, no fouling will grow there. So that means we have we do not need biocides, for instance. We use the pH gradient to take away the scaling, initial scaling, and also completely disable any biofilm to grow. So that's actually a twofold action we do. And now, we do this about 2 times a minute. We can do this pH swing, and that means the compartments, the left chamber and the right chamber, they will remain clean. And that's actually the purpose of doing this. And I know the technology to make chambers, that's another thing I didn't discuss, the technology to make chambers inside this heart of the alkaline electrolysis cell, that is another thing. I did not discuss this, but that's when you really want to have a technology out of this, you need to do additional steps. But that we learned from 18 years salinity gradient energy, what you have to do actually there to make it run without any issues. But
my question is how do you need to do this pH switch so often, or can you do
no,
it?
when you really that's a good question. I showed that you can do it twice a minute. You can also do it twice per hour. But in this case, it's like cleaning your teeth twice every minute. And it's cleaning your teeth. I mean, at home you clean your teeth normally twice a day. Could also be twice a day. It's a good question, Martin, because I clean it now twice a minute. And you will find easily people who clean their teeth twice a minute, 24 hours a day. That would give you very clean teeth. So you can imagine how clean the inside of these chambers remains when you clean them twice a minute. So it's actually top of the bill cleaning. And I agree with you, could be, the frequency can be less. This is really a high frequent cleaning, keeping it absolute clean, not giving it any chance at all. I mean, biology is fast, but it can't grow in half a minute.
Yeah, because then I don't know how this will influence the hydrogen production of your system exactly.
No, not at all, because the hydrogen and oxygen production, that is done at the anode and cathode. And you don't interfere at all with these processes because they are kept apart. And they are kept apart in a pure way because I run typically at 1500 amps per square meter. That's another thing. And very high selectivity for your proton transport and hydroxyl ion transport through the bipolar membrane. So the co-ion transport, actually the forbidden transport in the bipolar membrane, is very, very low at this high current density. And actually that is a bit of the technology. The technology of the bipolar membrane we are also developing. So a key component in this whole setup is actually bipolar membrane, and you want to develop a bipolar membrane to your own specifications that runs at high current density. And this is just to show, this is actually bipolar membrane that normally runs at 1000 amps per square meter, where we don't, but I put it at 1500 amps per square meter because an unwritten law is you can go to 2000 amps per square meter, but the setup allowed us to run at 1500 amps per square meter. Yeah.
Okay, thank
So
you.
you had a good question, Martin, about how often you have to clean.
Thanks.
And I clean only twice a day my teeth, so not yes. Yes, other questions, please.
See a hand up.
Yeah,
Yeah.
on the mark, yeah.
Thank you, Michel. Can you hear me?
Yes, I can hear you, yes.
Okay, I'm speaking all the way from Nigeria. My name is Adekunle. So, yeah, I am a friend to HAT as well. I find this topic quite intriguing.
Yeah.
And I thought I should learn a bit more about what is going on because, yeah, I've been involved in the green hydrogen space and I mean, trying to find solution to the many challenges, the electrolytes, access to clean water and all of that.
Mm-hmm.
So my question is, okay, what is the path to scalability? Right now, I think it's at the R&D stage.
Yeah, well, the
What
size
is the
is...
potential to scaling?
Yeah.
At the current stage, what volume or what is the efficiency of the system? I was thinking also, how does it compare in terms of material use? I think, yeah, there's some positive advantage to material use because they're compared to PEM, the catalyst and all of that. But generally, the energy efficiency, I assume that there will be additional energy requirement compared to the normal electrolysis, alkaline electrolysis that we know.
Mm-hmm.
So I think I'm just trying to find out how much more work needs to be done to see this technology at scale, at deployment and all of that. Thank you.
Yeah, I understand your question. First of all, this is one of the examples we are doing, because we have other ways we can put our electrolysis cell to get the same hydrogen. So there are other ways. And now, first of all, I want to comment on the proton exchange membrane electrolysis cell technology and the anion exchange membrane technology. Now, yeah, actually the alkaline electrolysis cell that uses a kind of porous separator. I want to say that both technologies, they have been put forward as commercial systems, but they are still lacking, you know, with some issues. And one issue is the crossover of hydrogen towards the anode, where oxygen is being made. I think you should not put a system in the market that does not allow you to operate at zero current after you had current on it. So when you have a windmill or a photovoltaics, and when the sun is away or the wind is away, you do not have power generation. And actually these systems, you cannot switch off the current. So I would first say, try to find a system with as low energy needed as possible, where you can switch off the current any moment without endangering you and your system. That's my first comment. Second comment is, indeed we should not use platinum group metals, and that leaves us with systems where we want to use seawater without desalination. Here I've shown one example. There are other examples we have in the lab here that use less energy. And also I have to say that we did not use here any electrocatalyst. So an electrocatalyst at the anode and the cathode will lower finally the cell voltage. So I think the scale we did it here, the example I showed at 1500 amps per square meter was with electrodes of 20 by 20 centimeters. And that's a single electrolysis cell. The single electrolysis cell can of course be stacked and you get a bipolar configuration, I mean electrically bipolar. The size of the cell can also be larger, but you have to see it in terms of how much hydrogen of course you want to make. It's of course lab scale, but it's not on a 1 square centimeter scale we did it. We did it on 20 by 20 centimeter electrodes, and that's 400 square centimeter. So that is a bit larger electrochemical cell. The current was 60 amp, that is not a very low current. I see electrolysis cell 1 square centimeter, we have the 400. So it's a bit higher up in scale. And yeah, I think when you might want to make a stack, I mean, stack means cells in series, it's possible. It's possible. And when you would want to enlarge the cell, you can enlarge the cell somewhat. We know, of course, from Redstack, a company in Snake here in the Friesland, in the Netherlands, they make large electrodialysis stack, for instance, seawater desalination, and they use electrodes that are a bit like 44 by 44 centimeters, so they're a bit twice as large as I did in the dimensions, so 4 times the area. So that's a bit how far you could think you could scale up, but then you need to stack. And well, this is one technology. There are other technologies possible, also based on bipolar membrane technology. So I have now 2 students, and 1 master student is working on bipolar membrane technology to introduce electrocatalyst and to go to as low cell voltage as possible. So my answer is, we see it's working. We have to upscale it, but that can only be done when it works at a smaller scale, and I see it's working, so upscaling should be possible. Stacking is another thing, because you need to do it in a bipolar configuration, and that's always, you need a bipolar plate, so that is, would be, for the alkaline electrolysis, else we do a nickel plate, so that is also a possibility. And yeah, we need, and that's always needed, a company that takes up the technology and discuss with us what technology, because we have different technologies for the same demand, making hydrogen, are possible. So we need to discuss. So that's an open invitation to companies who would like to talk about this technology. And the technologies being developed so far in the world, we see technologies being developed that do not work, for all kinds of reasons. And we try these technologies as well, or we study really what is happening there. We see that there are issues. So we try to also either to solve these issues or to make our own technology. That is actually my answer. No, I don't hear you.
Great, thank you.
Oh, you're there, yes.
Yeah.
Yeah.
So compared to, I mean, the normal alkaline electrolysis, the other part is the uptake of the brine, the retrieving of the salt, sodium chloride, and then the possibilities for other applications. I know sodium chloride has several other applications, whether as sodium or as a chloride. And
You mean for desalination?
the extraction of those materials and the potentials, because ultimately, at scale, you want to look at the technology, the efficiency, and that's what will support the uptake of the technology and the future applications.
Mm-hmm.
So I don't know if you have talked about, if you can talk about all of these.
I know that.
That will possibly present a business case and the advantages of this technology over several others. As you know, I mean, alkaline itself normally is not optimal with intermittent energy source.
No.
Compared to PEM. So that is one disadvantage. Is this in consideration? Because I mean, if you want to choose between PEM and alkaline, I mean, usually the efficiency is higher, and then you talk about adaptability to intermittent energy sources.
Yeah, I agree. But with PEM electrolysis, as I tried to explain, there are 2 issues. 3 actually. The loading, I mean, how much catalyst is on every square centimeter, what is projected by the European Union, and what they think is the lifetime, that combination keeps the catalytic activity, but for a much shorter lifetime. Because I worked 14 years in magneto special anodes, and you know, it's not possible. You can put 40 times less noble metal at your anode, and you have the same catalytic activity, but your lifetime, you know, your wear rate, that's the problem. So I do not know why people with an economical background suddenly decided you can have 20 to 40 times less noble metal loading and keep the same lifetime. It's not true. They can put it on paper, but it's not true. Another thing is that the platinum iridium is not available in the world. So I know people really like the PEM electrolysis cell, but this same electrolysis cell you can't shut down because of the crossover of hydrogen. But it's more that the lifetime prediction is not true. It's a kind of, targeting you cannot reach. When you want to have much more lifetime, to double the lifetime, and 20 to 40 times less catalyst. I mean, you have to be realistic. When that was true, companies like the Nora in Italy and Magneto in the Netherlands and China would have done that years before, much less platinum in iridium coating, and say to the customer, we guarantee the electrode with 40 times less loading. But it's not true. It's not true. So these projections are not true. And now, because I work there, and we laugh about it. So what is this? So that's why you better go to an alkaline system where there are no platinum group metals. So this whole discussion you will never win unless you're from the inside to say, we love about this statement about lowering the loading. So you go to the alkaline electrolysis system and then you see, you actually make use of a high pH environment. So with this high pH environment, we can also make other systems like shown here with half of the energy use. So that you can put already in your pocket, half of the energy use. And that's what we are working at the moment. And as said, we make our own bipolar membrane at Wetsus. We had a PhD on it and we get a new PhD. We are scaling up and trying the best, make the best bipolar membrane in the world up to 5,000, 10,000 amps per square meter, because the footprint we want also to make small. And when you have a small footprint with a small installation, you can make more hydrogen as we do now. And well, I went up to 1,500 amps per square meter, but the first target we have is 5,000 amps per square meter with bipolar membrane electrodialysis of seawater in another configuration I've shown here. To say we get some volt below the value because we want to go to perhaps 2 volt lower as we have shown here, or a bit more. So we work also on what you say, less energy use, but still making use of the fact we use seawater. And the whole discussion with the platinum group metals, platinum iridium, I think it's not true. It's absolutely not true. They can put it in Europe and they say, well, this is a target, but it's not true. So we get away from that discussion because that's scientifically not true. Yeah. Now I see you even live on the screen. Yeah.
Yes, indeed. I agree with you in many ways, really.
Yeah.
Because with the PEM technologies, of course, there are many challenges.
Yeah.
Yeah, right now people are only talking about the efficiencies, and I think that in the long term, alkaline technology will be the overall winner, because ultimately what I say.
Yeah.
But with this technology embedded, I'm sure that it would take alkaline even a lot further than what we currently have.
Yeah, and we are now.
Thank you very much.
Yeah, with one student I'm working now on the alkaline technology in an adapted state. So also that we try to go lower and lower in voltage and still use seawater. So that's another way. So I didn't. That is a bit of a hybrid way of working, but did not show that. So there are a lot of possibilities. Thank you so much. Are there other questions? Otherwise, we close the meeting. Yeah? Okay, thank you so much. We're going to close the meeting here. It means we stop also filming. Thank you so much.
Thanks, Michel.
Yeah, thank you.
Thanks a lot.
Yeah.
And have a good weekend.
Yeah, have a good weekend.
Thank you. Bye.
Bye. Bye-bye.